Hello friends, in this video, we should design a sequence detector Mealy Fsm using JK flip-flops with overlapping method to detect the sequence of bits 11011. In this, the sequence detector means it is a sequential circuit used to detect the sequence of bits in a given input sequence. Whereas Mealy Fsm means it is one type of finite state machine model. In this, the output depends on previous outputs and present input. Here, we should use JK flip-flops to design this sequential circuit, and we should follow the overlapping method. To understand this concept of sequence detector, let us take one example. Here, this is the input sequence having stream of bits. In this sequence of bits, we should identify the sequence of bits to be detected. Starting from left side, first to identify, this is the first group. Next, the second group is 11011. This is the second group. Here you can see these two bits should be available in first group and also in second group because here we are using overlapping method. Similarly, the next group is 11011. This is another group. Okay, only three groups we have. Okay, now based on this, we should identify the output 1. After completion of detection of 5 bits only, we will get the output 1. Okay, here you can see this is one output at this place because all the 5 bits are detected. Next, here also you can see the output is 1. Okay, the remaining all bits in the output sequence should be 0. So this is the output which is indicated by the variable z. Okay, this is the sequence detector concept. Now we should use this concept to design the circuit diagram. Okay, here we should follow the design procedure to develop the circuit diagram. The first one is identify the number of states and flip-flops required. Second one is state diagram. Third one is Mealy transition table. Fourth one, state table based on the Mealy transition table, and use excitation table to write the flip-flop input values. Next obtain simplified Boolean functions using K-maps. Finally, draw the Mealy Fsm logic diagram for sequence detector with the help of Boolean functions. Now we should follow step-by-step procedure. The first one is sequence of bits to be detected are 11011. Here, the number of bits in a given sequence should be 5. So the number of states required are 5. Okay, and those states are labeled with S0 to S4. Now we should identify how many flip-flops are required to design the circuit diagram. Here we have S0 to S4 means so totally 5. 5 means 0 to 4 only. The highest number is 4. In binary form, it should be written as 100. That means it requires totally 3 bits. So 3 flip-flops are required to design the circuit diagram. Or you can see here the sequence of bits for these 0 to 4 numbers also should be written as 000 to 100. Based on these values also, you can identify the number of flip-flops required should be 3. Now we should develop the state diagram. To develop the state diagram, first we should take the number of states. Here we have totally 5 states, S0 to S4. Next, connect all these states. And then assume the first state as the initial state or reset state. Next, place the first 4 input bits on these lines. Here the input data is 11011. So that we have to place only 11011. Okay, later we should fill the last bit also. Okay, so here the first bit is 1, second bit is 1, third bit 0, fourth bit is 1. Okay, and in the denominator we should write the output value. All the output bits are zeros because when all these 5 bits are detected, then only the output will be 1. Otherwise, the output is 0. Here only we are taking 4 bits. That's why the output should be 0 for all these bits. Next, we should write the input bits for all these states. For the first state, the input bit is 1. For the second state, the input bits are 1, 1. For S3, 1, 1, 0. For S4, 1, 1, 0, 1. 1 by 0 means it should be designated as x by z. X is the input, z is the output. Here x means this is only single variable. That means 2 power 1 combinations of binary we can assign. Okay, 2 power 1 equal to 2. That means 0 and 1 only. Okay. Here already we have taken x equal to 1. When x equal to 1, S0 goes to x1. Now we should find the next state for S0 when x equal to 0. The initial state always goes to self state only for x equal to 0. That's why it goes to self state only when x equal to 0. Then the output is 0. Okay. Now coming to the S1. For S1, the input bit is 1. And when x equal to 1, it goes to S2. Now, when x equal to 0, we have to find the next state for S1 now. For that, we should place the 0 at this place because we are searching for x equal to 0. Now, we should check whether S1 goes to self-state or not. To check whether it goes to self-state or not, we have to compare these two bits. If these two bits are matched, then it goes to self-state. Otherwise, it goes to reset state. Here, these two are not matching. So that it goes to only reset state. When x equal to 0, then the output is 0. Similarly, for S2. For S2, the input bits are 1, 1. And when x equal to 0, it goes to S3. Now, we should find for x equal to 1. Okay, so that we should place 1 at this place. Now, we should check whether S2 goes to self-state or not. For that, we have to compare the input bits with the last two bits. Okay, if these two pair of bits are matched, then it goes to self-state. Yes, here these two ones are matched with these last two 1 bits. That's why it goes to self-state only. Okay, so this is the self-state indication. With x equal to 1, then the output will be 0. Okay, next coming to S3. Here also the input bits are 1, 1, 0. When x equal to 1, it goes to S4. Now we should find for x equal to 0. So that we should place 0 at this place. Now again, we should check whether it goes to self-state or not. For that, we have to compare the input 3 bits with the last 3 bits. If these 3 bits are matched for these 3 bits, then it goes to self-state. Otherwise, we have to compare with the previous state. Okay, S2. Here, these two are not matched. That's why we should compare with the S2. The input bits for S2 are only 1, 1 in red color. Okay, so that the last 2 bits should compare with these 1, 1. Okay, suppose if these two 0, 0 bits are matched with this 1, 1, then it goes to S2 state. But here these two are not matched. Now again we should check with the S1 now. Okay, here for S1 the input bit is only single 1. Okay, so that we have to compare with the single 1. Okay, so to compare with the single 1, only we have to take the rightmost bit only one single 0. Okay, if these two are matched, then it goes to S1 state. Okay, otherwise, finally, it goes to reset state only. Okay, when x equal to 0, then the output is 0. Okay, next, coming to S4. For this, the input bits are 1, 1, 0, 1. Here, two combinations we have to check. If x equal to 0 and x equal to 1. For both combinations, we have to check the next state. Okay, first we should take the x equal to 0. Okay, first we should check whether it goes to self-state or not. Again, we should follow the same method. We should check these 4 bits with the last 4 bits. But here, these two are not matched. Okay, next we should compare with S3. Okay, S3 input bits are only 1, 1, 0 in red color. Now we should take only rightmost 3 bits. These are 0, 1, 0 only. Okay, rightmost 3 bits. Now we should compare. If these two are matched, then it goes to S3. But here these two are not matching. Okay, again we should compare with the S2. Okay, S2 bits are only 1, 1. So that we should take only 1, 1. This is S2. Okay, so to compare only 2 bits, the rightmost 2 bits only we should take. Okay, 1, 0. So 1, 0 and 1, 1, these two are not matching. So that it doesn't go to S. Next, we should check with the S1 now. Okay, here S1 is only single 1 now. So single 1, this is S1. Now should take the rightmost bit 0 only. These two are not matching, so that it doesn't go to S1. So that it goes to only reset state only for x equal to 0. Then the output is 0. Now for x equal to 1, we have to check whether it goes to self state or not. For that, we have to check these 4 bits with the last 3, 4 bits. These two are not matched. That means it doesn't go to S4. With should compare with S3 bits. S3 bits are 1, 1, 0. Okay, you should check the last 3 bits. 1, 1, 0 and 0, 1, 1. These two are not matched. Okay, next S2. Here 1, 1. So here for S2, the input bits are 1, 1. You can see the last 2 bits also 1, 1. So that it goes to S2. S4 goes to S2 when x equal to 1. Then the output will be 1. Okay, you can see here S4 goes to S2 When x equal to 1, then the output will be 1 because the detection of all the bits should be completed with this last x equal to 1. Okay. This is the state diagram for the given sequence of bits 1, 1, 0, 1, 1. Okay. If you develop the state diagram correctly, then it is easy to develop the circuit diagram. Suppose if you have done any small mistake in this state diagram, the remaining part totally it goes to wrong. Okay. Now let us move to the third step. With the help of the state diagram, we should develop the Mealy transition table. This is the Mealy transition table. In this, we have present state, next state, output. Present state should be represented with the letter Q, next state Q plus output Z. We should find the next state values for input value x equal to 0 and x equal to 1. Similarly, the output value also for x equal to 0 and x equal to 1. Here, first we should list out the states S0 to S4. Then we should write the next state values with the help of this state diagram. Okay, starting from S0, if x equal to 0, it goes to self state. So that S0 goes to S0 when x equal to 0. When x equal to 1, it goes to S1. Okay, so that it is a S1. And in these two cases also, the outputs are zeros. In this way, you should fill all these rows. Okay, you can see here S4. For S4, when x equal to 0, it goes to a reset state 1, S0. Okay, for x equal to 1, it goes to S2. Okay, and the outputs should be here, this is 0. When x equal to 1, it goes to 1. Okay, this is the Mealy transition table. Now we should assume the binary values for these states. For S0, the binary value should be 0, 0, 0. Similarly, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. The 3 bits. Next, we should develop the state table with the help of the Mealy transition table. Okay, well, in state table, we have different columns. So the first one is the present state, it is Q. Present input X, next state Q, flip-flop inputs are excitation values, JA, KA, JB, KB, JC, KC. Next output is Z. Okay, and then write the equivalent decimal value. Now, this is the Mealy transition table. With the help of this Mealy transition table, by assigning the binary values to each state, we should fill all these columns. Okay, now we should see the first state S0. S0 is 0, 0, 0, the binary value. When x equal to 0, it goes to 0, 0, 0. Okay, next S0, it goes to S1 when x equal to 1. That means when x equal to 1, 0, 0, 0 goes to 0, 0, 1. In this way, we should fill all these rows. Okay, just you should write easily first this one, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10. In this way, this is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. In this way, we should write all this. The easy way of writing is first we should fill the first column with the S0, S0, S1, S1, S2, S2, S3, S3, S4, S4. Okay, because S0 for x equal to 0 and x equal to 1. Next, S1 for x equal to 0, x equal to 1. Similarly, S2. This is S3. This is S4. Okay. Next, we should write these values sequentially manner. S0, S1, then S0. Next, S2, next S3, next S2, next S1, next S4, next S0, next S2. In this way, you should fill all these columns. Next, we should fill these flip-flop input values. Okay. So, how many pair of flip-flop inputs required? Here, 3 pair of flip-flop inputs are required. Okay, because here we are using 3 flip-flops. Okay, JA, KA, JB, KB, JC, KC. To write these input values, we should take the excitation table of JK flip-flop. The excitation table of JK flip-flop says that present state, next state, these two are input. The outputs should be flip-flop inputs. So 0, 0, 0, 1, 1, 0, 1, 1, because the 2 inputs we have, 4 combinations. Okay. Now for 0, 0, the excitation values are 0, don't care. For 1, 1, x0. This is the easy way of understanding. Okay, 0x, x0, opposite. Similarly, for 0, 1, this is 1x. For 1, 0, this is x1. These two are just opposite. Okay, you should, in this way, you should memorize this table. Okay, to write the JA, KA values, here already I have given different color combinations. For blue color, you can see to write the JA, KA values, you should focus on the present value of A and the next state value of A. Okay, that is A plus. That means 0, 0, 0, 0 means here 0, don't care. So this is 0, don't care. Next 0, 0, again 0, don't care. In this way, you should fill all these rows. Similarly, JPKB. JPKB means we should focus on this B and B plus. Similarly, C and C plus. Okay. In the same way, we should fill the output. The output is 1 for the last combination only. So that you should place only 1 at this place. That meaning all the bits should be 0. Okay, so this is the state table. Easily you can write. Next, you should write the equivalent decimal values. This is 0, 0, 0, 0 because up to present input, all these are inputs only for the state table. Okay, so 0, 0, 0, 0. The equivalent value is 0 because the binary bits are 1, 2, 4, 8, 2 power 0, 2 power 1, 2 power 2, 2 power 3. So based on these binary bits, we should write the equivalent minterm number. So the last combination is 1, 0, 0, 1. So its equivalent value is 9. Okay. Here we are using 4 bits every time. So with 4 bits, totally 16 combinations of binary we have to fill. But we are using only 0 to 9, totally 10 combinations. Okay. So out of these 16, we are using 10. So the remaining 6 combinations should be taken as don't cares in K-maps during the finding of simplified Boolean functions. Next, we should write the Boolean functions in terms of minterm values based on this state table. You can see here I have written all these Boolean functions in terms of minterms for output variables of state table. So for JA, we have 1, don't care, don't. So we should take the equal minterm numbers for ones and don't cares. For 1, its value is 7. Okay, so sigma m of 7, this is the minterm number. The remaining 2 are don't cares only. Okay, I am writing SOP forms. Okay, so here for 8 and 9, already we have discussed from 10 to 15, all the minterms should be indicated with the don't cares. So that along with these 8 and 9, we should write the remaining 10 to 15 for all these combinations. Okay, next for KA. For KA, you can see here these 2 are ones and the remaining all are don't cares. Okay, so 8 and 9 are ones, sigma m of 8 and 9 minterm numbers. The remaining all are don't cares 0 to 7 and 10 to 15. This way we should write the Boolean functions in terms of minterm numbers. Even for output also, we should find the simplified Boolean functions with the help of the K-maps. First, we should place the ones and don't cares in these minterm number boxes and then make groups. For this one, only one group is possible with the don't care. The remaining don't cares need not to make a group. For this group, we should write the simplified Boolean function. This group lies in these 2 rows and this column. In these 2 rows, for A, 0, 1, so that A should be skipped. For B, 1, 1, 1, 1 is common. So its equivalent value is B. Here 1, 1, 1, 1 means this is C and X because here the variables are AB and CX from state table. Okay, so the product is BCX. Now we should write the equivalent Boolean function. Next for KA, you should place the ones and don't cares. Here you can see all the minterm boxes are filled with either ones or don't cares. Okay, now we should make as one single group with all these ones and don't cares. Here, because all these are adjacent each other, okay, so that it is a 16 ones group. This group lies in all these 4 rows and 4 columns. Okay, so both AB are skipped and CX are skipped, so that the equivalent product is 1 into 1 should be 1 only. Okay, next for JB, KP, same procedure you should follow. For JB, you should place the ones and don't cares and then make groups. Here you can see this is the first group and this is the second group. For this first group, you should write the product term as AX. This group lies in A in these 2 rows and in these 2 columns. Here A is common and in these 2 X is common, so that AX, so that AX. And for the second group, this group lies in these 4 rows, so AB should be skipped and it lies in third column, so that its equivalent is CX. Okay, so that its equivalent product is CX. Therefore, it should be written as A plus C into X. X is common. Okay. For K, similarly for KB, you should fill the minterm number boxes. Then we should make as a group. This is one group. This is 8 ones group. We should write the equivalent product. This group lies in all these rows, so that AB should be skipped. And in these 2 columns, we have C is common because for C, the binary is 1. Okay, so KB equal to C. Next, JC. Same procedure we should follow. Here, these 2 are adjacent with these two, so that it is one group, and these two are adjacent each other, so that it is another group. For this two ones group, 0, 0 means A dash B dash. Here X is common, so that A dash B dash. And for this 4 ones group, here B is common. B first column and last column, we have X dash, B X dash. For KC also, all the minimum number boxes are filled with either ones or zeros. So it is a single one group, so that its simplified value is KC equal to 1. Similarly, for Z also, we have only one single one, and 10 to 15 are don't X. So the equivalent simplified Boolean expression is Z equal to Ax only. Okay. With these simplified Boolean expressions, we should develop the circuit diagram like this. Okay. So to develop the circuit diagram, first we should take the 3 flip-flops. This is first flip-flop, second flip-flop, third flip-flop. The name of the flip-flop is A, so output should be specified with A dash, B dash, C dash. Next, for JA, BCX. This is a 3 input AND gate. So BCX. So B nothing but the second flip-flop output, C is the third flip-flop output, X is the external input. Okay. In this way, we should connect the remaining all combinations, including Z. Here you can see Z equal to AX. Z equal to AX means the output depends on A means past output, X is the present input. So it depends both on past value of the output and present value of input. That's why it is the Mealy type of the effect. So in this way, we should develop the sequence detector circuit to detect the sequence of bits 1, 1, 0, 1, 1. I hope you understand this concept very easily. So please practice thoroughly. This problem is very, very important either in a GATE examination or in your undergraduate examinations. Okay. So if you are watching my video first time, please like, share and subscribe to my channel DLD Plus. If you have any comments, so please comment in comment box. Definitely I will help you. Thank you.